Did we get all the way to the point where we had all the motion equations written out? Did we talk about using omega for square root of k over m? Did we talk about the fact that the units of omega are radians per second?
Yes.
All right, so that's right where we ended up. Excellent. So this all started from the idea that if you have a Hooke's law restoring force and you combine it as the only unbalanced force with an object with inertia, that it generates a series of equations by solving the second order differential equation related to it. And I'm going to write it, I'm a little bit behind, so I'm going to skip over the part where I write square root of k over m everywhere. I'm going to skip over the part where I write square root of k over m everywhere and erase it and write it this way by just going right to the result that I would like you to know. That is the solution to the differential equation where I have k over m times x equals the second derivative of x with respect to t. This is the direct result, and that creates this idea that omega is square root of k over m. So if you have this, it generates this. More importantly, if you have that, it generates a few other things. And we talked about all of these, but like A max is x naught omega squared. And V max is x naught omega. And we talked about the fact that you can prove that. You can prove this with Newton's second law. That is basically right here. What happens if you solve that for A? And you get this by looking at conservation of energy. So we showed both of those yesterday. In addition, we talked about how long it takes for the system to oscillate. And we said that, 2 pi times the root of m over k, but putting it in this notation, it's 2 pi divided by omega. And that also means the frequency, which is the inverse of the period, is omega divided by 2 pi. And this is really where you can see the reason why we call omega the angular frequency. This is the oscillatory frequency. It would be in oscillations per second, but if you divide the oscillations by 2 pi, you get, if you multiply the oscillations by 2 pi, you'd get radians per second. And that's why you take the radians divided by 2 pi, and you get oscillations per second. So all of this is predicated on the idea that omega is equal to the square root of k over m, and that came from a second order differential equation. Now, that's a lot, and I don't want to somehow assume that this all makes perfect sense, why I'm writing it like this. So let me impress upon you something that's important. The spring mass example is the model upon which all other simple harmonic motion is based. So once we've created this model, anytime we have a restoring force that's linear, anytime, you just plug in whatever the value is for k everywhere here, and you get a new set of relationships for that particular system. There are lots of systems that oscillate. So if you can isolate the forces on that system, you can predict how it will oscillate before you build it, before you put it together. All you have to know are what the forces are that are going to act on it. And we're going to do that here in just a minute. So to understand this, I need you to understand one more thing, and this is for the new folks to physics, and you guys who are old folks to physics. Keep in mind over here, the sine function is 0 when time equals 0, but the moment we are no longer at time equals 0, there is an explicit negative sign here to tell us that our velocity will be in the opposite direction of the displacement. So we pulled it out, that was positive direction. The moment we let it go, it moves in the negative direction. All of the negatives and positive signs match up with what we expect. The acceleration continues to have that negative in front of it, meaning that I pulled it to the right, the acceleration at time 0 is to the left. So those negative signs aren't arbitrary, they're explicit. And they're based on the original direction of the displacement. This is actually a vector. And the rest are all vectors as well. And their vector direction is preserved in the equations. Expressions for x and v. You can join me if you'd like, but I want to talk about this right now from the standpoint of how AP problems tend to worm this stuff into their problems. And so I'm using this because this has a certain ability to hold on to specific stupid details I think you should know. I've recreated one half of an oscillation here. So if you take and draw a line straight down the middle of the paper, so that line is basically marking where equilibrium is. Our top picture here is actually the relaxed state of the system. So I've not added any energy to the system or anything. It is just the relaxed state of the system. So I'm going to kind of focus on these first parts there. So when I say the relaxed state of the system, what I'm trying to indicate is that at this particular moment, the net force is 0, and I have added no energy to the system, so there's no energy at all in the system. Equilibrium is defined as when the system has a net force of 0. It's not defined by the relaxed state of the spring. Why would you even say that, Mr. Shelton? Because this is the relaxed state of the spring. If I put the mass on it right here, this is not the equilibrium position. Because if I were to let it go, it wouldn't stay here. The equilibrium position for a vertical spring will be when the two forces are balanced. This is the equilibrium position because the net force is 0. So when it's set into oscillation, it behaves like a simple harmonic oscillator, but it's different. The forces are all different here because gravity is acting on the system the whole time. Although it is bobbing back and forth in either direction around the equilibrium position, the spring is never in its relaxed state. The spring is always pulling upwards to counter gravity. So this is a simple harmonic oscillator, but the conditions upon which it oscillates are different than the sideways one. So when we talk about these things, we're using the simplest example first, because every other example probably has a certain tweak or a certain complication that makes it a little bit different to observe. Does that make sense so far? Yeah. So that's why I'm saying things like, it's when the system is in equilibrium. That's why I'm saying it. All right, so first thing we're going to do is we are going to pull the object outwards a certain distance. We're calling this distance the amplitude, the starting position of the system. Now, I'm calling that x naught. I'm calling that also the displacement. I'm also calling it the amplitude. Be aware of one important detail here. I'm pulling to the right, so I'm saying the right is the positive direction. That's where I'm starting. And that's important because at this instant, I'm going to call this t equals 0. It is the moment I release the system. And at t equals 0, v equals 0. And at this exact moment, since I am at the maximum displacement, I must also be at the point where the maximum force is being applied. This is the furthest the spring will be pulled out. The force in the spring is based on how far it's pulled out, so this must be the maximum force. And since this is the only force acting on the object, this must also be the moment of max acceleration. So if you're ever on an amusement park ride where you're being flung back and forth, it's at the ends that you're experiencing the most acceleration, even though you're not moving. So keep that in mind. That's that part where you've got to flip backwards and go forwards. That's because you're not moving. Velocity is 0, but acceleration is max. It's actually quite a dangerous moment to be. Amusement park rides try not to create this condition because it tends to hurt people. So we don't use elastic very much in amusement park rides. Now, we release the system here. All the energy right now is in the form of elastic potential energy. We allow the system to move for a small moment. So we are no longer at t equals 0. The box has slid a little bit to the right, so now we're at a position that is less than the amplitude. We clearly have some velocity. And that velocity is negative. And there's no doubt about the fact that the velocity is negative. All right, the next couple things are, I think, obvious. There's still an acceleration this way. There's still a force this way. I think that's obvious. We are speeding the object up as we approach equilibrium. I know that's way down there towards the bottom. Sorry, all you people trying to see the bottom of the screen. There, is that better? Now, one more thing, and we didn't get to this yesterday, but the object's moving, so there is kinetic energy, but the object still has elastic potential energy. I still challenge you guys to plug in the right into the equations, the x, cosine omega t, and the x omega sine omega t. Plug them in there. Because when you work them out, you will find that the sines and the cosines cancel. Because you get a sine squared and a cosine squared, which add up to be 1. You should really try it out and see it work. Because it will all work out that this always equals 1/2 kx naught squared. The energy in the system is conserved. So at any time, if you know the position, you can figure out the velocity, not from the motion equation, but from energy, which would probably be easier. Energy doesn't tell you when these things occur, but it will tell you speed at position and position at speed. And we're going to be looking at some energy graphs later that I hate, and you will hate them too. All right, so moving right along. Continue my equilibrium line down here. Because this next place we're at, probably pretty important. All right. So in this next part, we are at equilibrium, which means net force equals 0. There's no force, no acceleration. The force is 0, the acceleration is 0. You guys recognize how much AP loves to screw with you. And this is one of those moments because although that's all true, velocity is at its maximum. So when velocity is at its maximum, force and acceleration are 0. And when displacement is at its maximum, force and acceleration are at its maximum, and velocity is 0. So an oscillator juxtaposes those values all the time. But there's something else here that's important. All the energy is in the form of kinetic, 1/2 mv max squared. All the energy's here, which we know also must be equal to 1/2 k x naught squared. But remember, we are at the position where x equals 0. We are at equilibrium. But also, and this is the most important thing I'm going to say because it's subtle, right now it is 1/4 of the period. That's how much time has elapsed. Because a full period is when I start at one point, go to the other side, and come back. So this is 1/4 of the motion. Now, think about this for a minute, please. If I did the reverse, if I pulled the spring in and released it, but the box wasn't connected to the spring and could leave, like a little box launcher. Do you follow what I'm saying? We've been doing problems like that all the time, where you pull the box back and I ask how fast is it going when it leaves the spring, and then there's a collision that happens later and all that kind of garbage. AP will slip in a question like, how long is it in contact with the spring? People don't think that it's a simple harmonic motion problem because they don't see anything oscillating. But they're using this. They're telling you that the box endured 1/4 of an oscillation while being launched. They're expecting you to calculate the period using that, since you can't calculate it using anything else unless you want to try and figure out the time using the sine or cosine function. You don't want to do that. So in any of these problems where a box hits a spring and comes to rest, and they ask how long did it take to come to rest, that's a simple harmonic motion problem. That's them slipping it in. It's probably only going to be 2 or 3 points, but those are the easy points to get. The equation's on the equation sheet. But they don't think you'll think like that. They'll think, well, it's not oscillating, so that doesn't, it can't be that. It's exactly that. So that's why I'm pointing this out, that it happens at 1/4 of the period. And be aware, there's several quarters of the period that seem appropriate. So I'm going to move on, because that's really about it that's important there. This next one, I don't have to say too much here, but I think there's only one thing I want to make sure you see. The velocity continues to be negative because of the way the sine function is. The sine reaches its maximum, and it's going underneath. The sine reaches its maximum in the negative direction, but it's still negative until it comes back to 0. So we still have a velocity in this direction, but the cosine function has switched. So now, suddenly, the force is this way. The spring is pushing on the object, and the acceleration is this way, because that's the direction of the net force. We still have 2 kinds of energy now, 1/2 mv squared plus 1/2 kx squared. And at this moment, the time is between 1/4 of the period and 1/2 of the period. Time's somewhere in the middle of that. And we now have a negative displacement. A negative displacement is why we also have positive force and positive acceleration. F equals kx. Now that x is negative, the force has switched direction. Until, of course, we make it to here, which is going to be back to x naught, but on the negative side. At this moment, force is again at max, acceleration is again at max, but velocity is 0, all the energy is back to elastic. And right now, we are at 1/2 the period. Now, usually, this is it. I don't do any more than this. If you look at half of an oscillation, you can pretty well do the other half on your own. And you probably don't need the other half to know what happens. Everything just switches direction, and the whole system begins all over again while I get that box back over to the other side. But I tried to make sure that as I did this, you understood that we're looking at the specific points of the oscillation and characteristics of it. It's the flow of energy I want you to pay attention to. It's the direction of forces. It's the time it takes. Remember, energy never predicts time. It doesn't have time in it. And time usually doesn't tell you much about energy. With oscillators, we have specific moments in time when we know the energy will be in specific places. You should come to know those moments. At 1/4 of the period, all the energy will be in one place. In the next quarter, all the energy will be in another place. And it's going to be moving back and forth between that. This is true for all oscillators, not just this one. So we're going to apply this to another oscillatory system. But this is a generic blueprint for all oscillators. So, now all of you folks who have been in all my classes, I like you to have something like this around. So that when you're dealing with these problems, you can kind of look at this and remind yourself where the energy is, where the forces are, and all that kind of stuff. Because today, what I really want to do is I want to introduce the simple pendulum. And the simple pendulum can be discussed more than one way. And I decided earlier today I was going to teach 7th period one method and 4th period another method and record them and just put them, but I'm not going to do it that way. I'm going to teach everybody the same method. In maybe a day or two, I'll bring up how you can do this differently. It's not easier. It's just different. I just generally find that you guys do better with linear stuff than angular stuff. So I'm going to do the linear conversation. But what we're about to describe can be done using angular work too. This is a rotating system. If you don't know what a simple pendulum is an ideal pendulum. They don't exist. They're fake. So let me be really clear from the start. A simple pendulum is not a mass on a string. Although whenever we do a lab and I say it's a simple pendulum, I've made you put a mass on a string. That's because a real simple pendulum is a point mass connected by a massless, inflexible rod. A string will bend. A string will stretch. And therefore, the length and the angle is always changing. So a string doesn't actually provide you with true simple harmonic motion. And neither does a real pendulum. I told you already, it's an approximation. But technically, a simple pendulum is a point mass at the end of a non-massed uniform rod. So a real pendulum, they behave different. And we're going to talk about physical pendulums tomorrow. So we're talking about the simple pendulum today. Now, here's what I want, and I have 18 minutes. I want to show you that all oscillatory systems can be replicated by the spring mass system. All you have to do is figure out how to show the force as a constant times a displacement, which is not as easy as it sounds. So that's what we're going to try and do. And to do that, I'm drawing this big so that you can see things clear. We want to study forces because that's where we started before. I want to deal with the forces acting in my system. That's what controls the motion of this system. I'm going to also identify equilibrium, because it is equilibrium that we compare to in all of our problems. I have a pendulum. I think it's swinging. This is not fixed. This is not me pulling it back and saying it's time zero. This thing is already moving, all right? I want you to understand that it is sometime in the middle of its motion, which means that at this moment, it is displaced some angle theta. At this moment, how many forces are acting on the pendulum? Go ahead. Gravity is definitely one. So I will draw mg. Yep. Tension from the rod. We're going to ignore friction and air resistance for now. These two forces must be contributing to the motion of the object. Now, pendulums are a little complicated. They move in 2 dimensions. Because of that, when I go to analyze this force, I have a choice of how I wish to set up my coordinate system in order to analyze it. So I'll ask you, do I want to set this up so that my coordinate system is this way? Or do I want to set this up so that my coordinate system is this way? Do I want to use the blue coordinate system or the red coordinate system? It makes a difference. And let me tell you, remember, ultimately, we are trying to compare this to F equals minus kx. X is a distance. So when I consider the blue direction or the red direction, what direction is the pendulum traveling? Is it traveling along the red direction or along the blue direction? If you're confused, let me just say it this way. Is it going to go this way at this moment, or is it going to go this way at this moment? And if you don't know, I'll have to help you. It travels in a curve, which means it's not going along that blue line. It's going along the red line. In fact, let's get all that stuff out of here for just a minute. This blue line, like that is not the path of the object. The path of the object will be something like that. Make sense so far? Now, I'm going to use the coordinate system that is based on the red line. So I'm going to put the red coordinate system back here, because that will help with our setting this up. But also, I'm going to have to throw some things in front of you that will be hard to remember. A pendulum is an object that's traveling in circular motion. So the forces are actually unbalanced in both directions. The tension is greater than the weight in the y direction. So that has to be, for it to travel in a circle, there has to be a radial acceleration. The issue that you need to understand is the radial acceleration isn't returning it to equilibrium. It's the tangential acceleration. The acceleration in this direction is the one that's returning it to equilibrium. That's the force we want to talk about. So to talk about that force, I'll remind you that there is a component of the weight this way. That is mg cosine theta. And there is a component, I'm not going to be able to do this. There is a component of the weight in that direction, and that is mg sine theta. Of the two accelerations, I want the one that is along the horizontalish direction, the one that traces the curve of the arc, because that's the force that represents the Hooke's law part here. That's what's making me travel along that path that is curved. So I want that acceleration. I'm saying it over and over again because we're going to run into a problem in just a minute. Our unbalanced force that we're going to look at is mg sine theta, and that equals ma. I'm going to have to prove this to you, but I don't want to. But I don't think it's hard. If theta is measured from equilibrium, meaning theta is measured this way, can you agree with me that a positive theta corresponds to a negative acceleration? That if theta is measured clockwise, the acceleration must be back in the other direction, counterclockwise. It's trying to go that way. So I want to make sure we understand that the acceleration is in the opposite direction of theta. So if theta is measured in a positive direction, I'm telling you that the acceleration is in the negative direction. We're trying to make sure we have a reason to make sure this negative sign exists. I said to you, our goal is trying to figure out how this looks like Hooke's law. And we're close. You might not believe it, but we have many of the properties of Hooke's law already. Remember, I have to show that minus kx equals ma. I got the ma, no problem. mg is a constant. K is a constant, mg is a constant. I have a constant times something that is about its position. Sine theta is about its position. The problem is that sine theta isn't a distance. And I need a distance. I need a constant times a distance, a displacement. But follow me. Would you agree that this is a triangle? So you would probably agree then that this little length down here and this angle and the length of the string probably are related. Let's call this, for just argument's purpose, x. I need a variable here. Is x okay with you? Because that would mean that sine theta equals x over L. Opposite side. I could substitute. If I regroup this, I have a constant times a displacement equal to ma. Right? That seems really close. There's only one major problem with this, and it's a big problem. The object doesn't travel along x. It travels along the arc length, s. Are x and s a similar length? How about this? What if I prove to you that there are times when they're similar and times when they're not? Do you know how to calculate s? Most students don't remember that we've done this already. Delta x is how much something has moved in an arc. S is the delta x in this formula. Theta is the delta theta in this formula. L is the radius in that formula. Bring all that together, and S equals theta times L. And X equals sine theta times L. So is X equal to S? Is sine theta times L equal to theta times L? What I'm really asking, apparently, is sine theta equal to theta? Remember, in this formula, right here, where is it, this one? Theta had to be in radians to use it. So we're not quite at the end of where I want it to be, but we're very close. So I've kind of shown you that these two are pretty close, aren't they? That's where we left off then. Got your calculators handy? You need them quick. Got 3 minutes. All right, here we go. I'm going to handle all the signs. You guys are going to do this. This table, everybody in the room is converting degrees to radians. That's multiplying by pi and dividing by 180. You guys are 1 degree. Yari, you're 2 degrees. Then back table there, 3 degrees. And let's see, 4 degrees. I didn't do 4. 5 degrees. 10 degrees, and along the back is 20 degrees. Got it? So, take a minute, whatever you were told to do, get her done, and let's go 4 places. I want 4 places. So, what is 1 degrees expressed as radians? All right, so what is 3 degrees expressed as radians?
0.1047.
Really? Try again. Three times 3.14159 divided by 180. I get 0.05236. What's 5 degrees in radians? Zero point what?
0.8726.
Now, I could keep going, but obviously I don't have time. But are you noticing a trend? There will be a point where we can't say this, but for right now, does it look to you like theta equals sine theta? This is called a small angle approximation. A small angle approximation. And it says that theta can equal sine theta for small values of theta.